let's dive further into motorcycle dynamics with Francesco Comolli, head of unit driving simulator DriSMi, alongside professors Massimiliano Gobbi and Gianpiero Mastinu from Politecnico Di Milano. In this presentation, he'll explore how motorcycle data enhances the reality feel on driving simulators. Discover innovative methods like the Intensino Plus system for measuring inertia properties and smart wheel technology for capturing tire characteristics.
Okay, thank you. I'm not Francesco Comolli. I'm older, but Francesco is here for the complaints. So, first of all, I will start describing this activity. Actually, I'm going to take a step back, let's say, with respect to what we have seen this morning. We have seen new driving simulators. We have seen simulation models, very refined models. The content of this presentation mainly refers to analyzing the motorcycle dynamic behavior in order to enhance as much as possible the reality feel that will be perceived by driving simulator users. Which are the main parameters of the motorcycle that affect the dynamic behavior? Inertia properties and tire characteristics. We already saw some works referring to this. So I will show you some systems that we are currently using for measuring inertia properties and to properly characterize the tire behavior. The focus will be in the near future to develop a driving simulator for motorbikes. And obviously, one key issue is fidelity. So be as close as possible to the real-world driving, which is even more difficult for motorbikes. My step back will be described in a few seconds. Let's refer to a very general driving simulation flowchart in terms of motion control. I have my driver, I have my vehicle model, I have the external environment, I compute the motion of the vehicle, then I have all the queuing which is necessary, and then a simulation motion control in which I have usually an MPC control in which I have a feed-forward and a feedback correction. Obviously, some information related to the motorbike that I'm going to include into this system will affect the performance of the simulator itself too. So there are two main aspects. The first one refers to the vehicle modeling, which is probably the most important one up to now. But when driving simulator, the colleagues showed us some very interesting results at the beginning of this morning, will be available, also the inertia property of what is actually on the simulator will be particularly relevant. Let's start with the modeling of the vehicle, the dynamic model. This is a slide that I use for my courses. We always have to remember that your model is not able to create information. It's able just to synthesize what you are providing to the model as data, okay? Parameters of the vehicle, tire force characteristics, and so on, okay? So this garbage in, garbage out has always to be kept in mind while performing a simulation or while developing your driving simulator environment. Referring to the inertia properties, this is the system that we have at Politecnico di Milano that could be used for properly characterize the motorbike with or without the driver. The system can measure rigid bodies from 5 to 400 kilograms. The dimension of the motorbike are acceptable. With one single test, it is able to obtain both the center of gravity location and the moment of inertia and the product of inertia. These slides, this and the next slide, will summarize some of the performance. I will try to make you understand if this level of accuracy is enough, fully satisfying or not for what we are looking for. The system is shown here. You see it's a simple, quite simple hardware in which we have these 3 bars which connect the rigid body that we are considering to an external frame. Each of these 3 bars is instrumented by means of one load cell and 2 encoders. Okay, so it's quite a simple layout. Just a few equations before lunch are important. So if I start from the generalized second Newton's law at whichever reference point on this rigid body, I can write the applied force as equal to the mass matrix times the acceleration, the generalized acceleration. This mass matrix depends obviously on the mass of the body, on the location of the center of gravity, and on the full inertia tensor. I can rearrange this equation into this identification equation that is shown below, in which you see for each time instant, I'm able to write 6 equations. But actually, the unknown parameters are 9. Location of the center of gravity, 3. Then the parameters of the inertia tensor, another 6. Okay? So for sure, I need more time instants at which I perform this identification, and by applying a very simple least square estimation approach, I can identify in just one test both the location of the center of gravity and the full inertia tensor. Okay? Actually, this is not the equation that is actually used in the system. We take into account also the deformability of the components to increase the accuracy of the identification. So the deformability of the carrying frame, of the bars, of the joints, and so on. The system is inside the quality certification process at Politecnico Di Milano. So we have a calibration, you see, body that can be reconfigured in order to check the quality of the measure that we are performing. It has been used for several different vehicle subsystems, and you see something that is similar to a motorbike, which is this racing sledge that is shown here. Actually, we are thinking of applying the same system to motorbikes. We have enough available room, and both in presence of the driver and in absence of the driver. Obviously, the presence of the driver, like we have seen in many presentations, has to be taken into account with different positions, relative position of the driver and of the motorbike. So, but the measure actually takes just a few minutes. So performing different tests could be affordable, let's say, in terms of time and money. So we can think about this. referring to the data of a motorbike, actually this data has been measured by a different system at University of Padova some years ago. And these are reasonable value for an example motorbike. What is important is not only getting the correct value of mass, location of center of gravity, but in particular, roll and yaw moment of inertia, and also very important, the roll yaw product of inertia, okay, for motorbikes. Because the coupling while performing transient maneuvers of the roll and the yaw is particularly relevant, and it significantly affects the motorbike dynamic behavior. Referring to the level of accuracy that I showed in the previous table, so plus or minus 1%, this is plus or minus 2 sigma, so 95 of the samples will be within this range. And for the product of inertia, plus or minus 0.5%, we are able, on this reference vehicle, to get an accuracy on the orientation of the ellipsoid of inertia below 0.2 degrees. That, based on many simulations, is more than enough with respect to what is generally required. Next step, okay, now let's say we are able to measure in an accurate way the inertia properties. Next step, tire characteristics, okay? It's clear to all of you that all the forces except the aerodynamic ones are exchanged between tires and ground, okay? So this information, like many of the previous presenters has already shown, is particularly relevant. For this reason, we developed measuring wheels, we call it smart wheel, that can be used, this is a very synthetic state of the art, for many different applications. Obviously, the simple one is I want to design my motorbike as light as I can, so I need the loading spectra for analyzing the actual behavior of the motorbike, or I need to define a simulation model that is as accurate as I can, which is the focus of what we are considering now. Okay, this is our smart wheel. It is based on a patented structure based on 3 spokes. You see 2 prototypes on the right side of the slide. Actually, it is made by using magnesium in order to keep the mass of the measuring wheel as close to the actual one. Actually, the mass of the wheel plus tire is very close to the standard one, okay? This system is able to measure the 3 forces, so longitudinal, lateral, and vertical, and 3 moments, so mx, my, and mz, you see at the center of the wheel. In the motorbike reference frame, so we have also the information about the rotation angle of the wheel, the absolute rotation angle of the wheel itself. We measure 6 quantities. From 6 quantities, we have a DSP that in real time is able to filter the signals and compute the actual forces, compute the actual forces in the proper reference frame, correct the effect of thermal drifts, and so on. This is transmitted wireless to a receiver on the motorbike. The receiver on the motorbike transmits this information to the CAN network of the motorbike itself. So this information is really available to the actual user of the motorbike. Actually, we are transmitting this information at 200 hertz per channel, but which is more than enough for all the racing and not racing application. You see the two wheels installed on a motorbike over there. Some details, you can find some details in many papers. Obviously, also in this case, the quality, the accuracy level that we required is relevant. You see this is a static calibration test rig that we are using in our lab for performing the static calibration by applying a large combination of loading conditions, because I have not yet emphasized, also the crosstalk has to be as low as we can. 1-2% is a reasonable target value. These are some data that we obtain in calibration. Remember, it's a 6-component system, so all the actions are applied at the same time, okay? And obtaining such good quality is not so easy. I want to emphasize this patented free-spoke structure allows to be not sensitive, not particularly sensitive to thermal deformation of the channel of the wheel itself, okay? Because it's a quasi-isostatic solution. This is a summary of the performance level that we can obtain on the forces. You see plus or minus 1.5 or 0.5%, and more or less the same, always 95% of the samples within this range for this specified loading situation. Okay. Then we perform also a dynamic verification on a specific rig that we have in the lab, and also in this case we have good results. And the final test, obviously, is on the motorbike, okay, in which the data are used, like Professor Faroni was saying before, in order to characterize in the proper way the tire behavior in the real scenario of the specific track that we are considering. I get to a conclusion because I think my time is, I'm running short of time. So, inertia properties and tire characteristics are paramount important for describing properly the dynamic behavior of motorcycles. On the basis of simulations, literature review, we can say that we need a level of accuracy for tire forces lower than 2% on both forces and moments. Okay, there is a shift, horizontal shift. Also, in terms of inertia tensor components, 2% of the moment of inertia is enough, but we need a very high accuracy on the product of inertia, because again, for motorbikes, it's really important the orientation of the inertia ellipsoid. We have the system able to obtain this level of accuracy. Step forward, thinking of what we are putting on the platform of our driving simulator in order to achieve low tracking error and reduce the power and the torque required to the control motors. We need to have a measure with an error less than 10%, okay, always to give you an order of magnitude. This level of accuracy will allow to obtain simulations and driving simulators able to provide the required reality feeling. That's it.